really moving it a little bit in the space. It doesn't matter so much what those things are anyway. So if I did swap them in this if I put this in a 4-dimensional space, I'm not really changing it that much either. Okay, so that's that's basically how these eigen decomposition relates to this singular value decomposition. They're very much the same object, and actually parts of how they're computed in these linear algebra libraries is actually very similar, because you're getting essentially the same objects out. There's one kind of, in most cases, the most stable way of doing this, and you use it to kind of often calculate both of these in some way. You need to kind of, you're called the eigenvalue decomposition, you're doing it on this P transpose P or PP transpose, so there are different ways of figuring out how to convert between one or the other, but you're using the same sort of basic operations to get the same sort of answers out. Okay, so the last thing on here is multidimensional scaling. And so multidimensional scaling is a similar problem where you're trying to do dimensionality reduction. And there's a final type that we'll talk about, I think, the second lecture after break, where you do these random projections. But this is a different way. You're not minimizing this cost onto a projection. What you're doing is you're saying, I have all these data points, and each pair of points has a distance between them. So I take these point set, and I convert it into this matrix, which is this is an n by n distance matrix, where the entry dij is the distance between pi and pj. Okay, so this is n by n, and everything is the pairwise distance, right? So this matrix is symmetric. It zeros along this diagonal because every point's distance to itself is 0, and everything else, every other coordinate in here has the distance between a pair of things. So MDS often will start with this distance matrix, or we'll start with the point set, and where you have this implicitly defined distance matrix. Then the goal of it is slightly different. It's to get to the goal is to go from either P, which lies in RD, or from this distance matrix, and to convert this to a point set Q, which is a subset of RK, where again K is hopefully much less than D. And your goal is to do it so that this distance matrix, if I calculated the same one in Q, that these are close to each other. So I want that. So the goal. There are different ways of defining it. So this is so this is kind of ambiguous. But I'm going to calculate this P is going to give me a distance matrix hat defined on these points, and I want this one to be close to this one in all of these things. So I can either look at the sum of the square distances or the sum of the distances. There are various ways of defining it. And so this is typically how MDS is defined, but it's not typically how people solve it. So when people often say, I'm optimizing, I'm embedding a point set in a small dimensional space, often in like a 2-dimensional space so you can visualize it. And I'm doing it so I want these distances to be close. But typically what they end up doing is they will actually they will take this distance matrix D, and they will do the eigen decomposition on it. And they will use the top 2 eigenvectors to project it into a 2-dimensional space. And that's not quite minimizing the distance between all the pairwise distances. It's really minimizing this function instead. It's doing a linear projection. So people are often using this kind of PCA approach to do something like MDS, The main difference between MDS and PCA, and at least in this way of defining it, is this will often start as just the abstract distance matrix. So you could start with Jacquard distance. So you could say, I'm defining Jacquard distance between a bunch of sets. I want to embed them in a two-dimensional space. And so we kind of saw this in the spectral clustering lecture, where we could define a similarity and then use the similarity to do that. So yes, so actually, so what they'll do is they'll so this are the distances. I actually want the dot products. So I'm sorry, I don't directly run the eigenanalysis on this. I do D. What do I do? D times. I do D transpose times D, and I get all the dot products, and I use those as similarities, and then I run the eigenanalysis on that. So I'm basically doing, I think it's doing the SVD on this, or the eigenanalysis on D transpose D. And so it's not exactly, so people will typically say they're trying to find the minimum projection that minimizes the difference between the pairwise distances, but they're actually more computing something that looks like this. But it works roughly the same way. Right, so okay, so hopefully, even if you've seen some of this before, you kind of got some new insights. After break, we'll talk about, instead of computing this on the full, very large data set, how do you do this much faster? How do you improve the runtime on this? And then we'll talk about various other things related to regression and dimensionality.